So number 2 says, consider the following equilibrium. We have HI, hydrogen iodide, decomposing to make hydrogen gas and iodine gas. And we notice everything there is in the gas phase. So this is, again, a homogeneous equilibrium. We're given the Kc value at 425 degrees Celsius. The Kc is 1.84. And then we're told, oh, and this is kind of irritating, isn't it? 10 grams of HI is put into, well, this is also irritating, 500 milliliters of flask at that temperature. Why do I say that's irritating? Because we need molarity. And you've given me mass, and you've given me the volume in milliliters. So that's going to be just a little bit more work for us to convert that to molarity. I'm going to use unit multipliers to do that, but you can also use the two little formulas that we've pointed out. Moles is mass divided by molar mass, and concentration is moles divided by volume. In any case, those things were put into the flask. What does that phrase tell me? They were put into the flask. Then those were the initial conditions, right? So initially, there was HI in the flask. It then says it was allowed to reach equilibrium. What mass of HI will remain at the end? Okay, so at the end, we want the mass of HI that will be left. So since you told me what was put into the container, and you're asking me how much will be there at equilibrium, that's the clue that we need to set up the ice table again. All right, so we're going to do the ice table. So I'll do that over here in the middle. So 2 HIs decompose to make H2 and I2. And we need to know the initial conditions for the ice table. Well, I know there was no hydrogen and there was no iodine put in there, so those guys are 0. But we need to know the initial concentration of the HI. So let's go off up to the left here, and I'm going to do that on the left side. So the HI concentration, square brackets, initially, I'll put a 0 beside that. So I'm going to take the mass, 10.0 grams of HI, and with, let me see, 1, 2, 3 unit multipliers, I'm going to get moles per liter, right? Molarity. Can you see what units we're going to put in here? We're going to try, first we're going to get rid of the grams of HI, and we'll switch that to moles of HI. Now that I have moles, I'm going to take the moles and I'm going to divide by the volume. So just divide means I put a 1 on top. The volume was 500 milliliters. So I'm just going to divide by the milliliters. But then I realize I can't have moles per milliliter. I need moles per liter. So my last multiplier, I'll put milliliters on top to cancel them out with the ones that were on the bottom, and I'll switch to liters. Okay? Let's just cancel out the units. The grams cancel out, the milliliters cancel out, and the units that are not canceled out are moles per liter, which means this will give me concentration. Ask now if there's anything there that doesn't make sense to you. So go ahead, I'll give you a moment's head start. Put in your numbers. 1 mole of HI, you may need to look on a periodic table. Remember, as I always say in class, don't just sit here and copy what I'm doing. Try to be engaged and do it yourself, and then ask me questions if you're not sure, okay? If all you're doing is copying me, you're not really understanding it. So this first unit multiplier is the molar mass of HI, right? 1 mole of HI weighs how many grams? We look on a periodic table, hydrogen and iodine, I get 127.91 is the molar mass. So that first multiplier, we're simply converting the grams to moles. Then we're dividing by the volume. because concentration is moles divided by volume, and the volume here was 500.0 milliliters. Now, some people might just want to, in their head, convert that and say, well, that's 0.5000 liters. And then you could just put a 1 over liters if you like. But I prefer to put this in and then show my work. The last multiplier, switching the milliliters to liters, there are 1,000 milliliters in a liter. All right, so go ahead and use your calculator. 10 grams divided by 127.91 divided by 500 times by 1,000. So my initial concentration is, how many digits can I keep? Well, 10.0 has 3 digits. The molar mass has 5. The volume has 4. So I can keep 3 digits, 0.156 molarity, or moles per liter, right? So that's my initial HI concentration. Let's go put that in the ice table. Now at this point, you're looking at the ice table and you realize we don't know any other numbers, right? There's no information in the question that tells me how much is there at equilibrium. There's nothing that tells me this percent reacted or anything like that. I have no other numbers that I can put in this table. So as we said yesterday, when you reach that point, if you only know the initial conditions and you don't know any other numbers, then that's the time to reach and use algebra, to use variables. So we notice on the right-hand side, they both begin with 0. So that tells me on the right-hand side, they both have to increase. So plus, plus. And if the right-hand side is increasing, then the left-hand side is decreasing. So we put a minus there. Now I'm going to use x's in here, but look at the coefficient. The coefficient of HI is a 2. So because it's got a 2, instead of saying that it loses x, I'm going to say that it loses 2x. Do you see the advantage of that? If somebody were to say that it lost x, that would be okay from a mathematical perspective. But if it lost x, what would the hydrogen have to gain? Hydrogen's coefficient is a 1. So if we were to say that HI lost x, hydrogen would have to gain half of an x. And suddenly we're using fractions in the ice table. And for many people, fractions are kind of irritating. So to avoid the fractions, since HI had a 2 in front of it in the balanced equation, instead of losing x, I say that it loses 2x. Now the hydrogen will gain half of that, so it gains 1x. There's no fraction. The iodine's coefficient is also a 1, so it will also gain x. Now at equilibrium, we can say the HI is 0.156 minus 2x, and we can say the hydrogen and the iodine are x's. Okay? Any questions about the ice table?
Yeah, can you just go over where you got x from, please?
So where I got x from, we're using x's because there were no numbers to put in the table after the initial line, right? When you read the question up above, the 10 grams in a 500 ml flask, that gave us the 0.156 molarity. And we knew there was no hydrogen or iodine, so those were zeros. But there's no other information in the question up above that would let me put any other number in the ice table. Do you agree with that, Yuri?
Yeah, yeah.
Since there's no other information, then I'm going to use x's to represent numbers in the table. So we said that if the hydrogen and iodine begin with zeros, they have to increase. And we said that meant the HI has to decrease. Is that okay?
Yeah, and then that creates
So then
yeah.
we looked at the coefficient for HI, and it was a 2. So we said, let's say that it loses 2x. Now the coefficient for H2 is a 1, so the ratio is a 1 to 2 ratio. So the hydrogen would gain half as much, so it gains 1x. And the iodine is also a 1 as a coefficient, so it also gains 1x. Are we good?
Yeah, it looks good.
All right, so now that we've got the algebra in, we need to set up an equation. And as we saw yesterday, the equation we'll set up is the Kc expression. So Kc is equal to, go ahead and write your equilibrium expression for that reaction. So concentration of hydrogen times the concentration of iodine divided by the concentration of HI squared. The Kc value is given in the question. So we get 1.84, that's the Kc value, is equal to, now at equilibrium, the hydrogen and the iodine are both x's. So you could say x times x, that would be fine, but x times x is the same as x squared. So I'm going to say x squared divided by the HI's concentration, which is 0.156 take away 2x, and that has to be squared. The Kc expression says that it's squared. So now we've reached a point where the chemistry gets put on pause and we have to do the math. We have to solve that equation. Do you notice something in this equation that works out just like yesterday for those who don't have a graphing calculator? The numerator here is being squared. The denominator is also being squared. That means we can simplify this equation by taking the square root of both sides. So if we take the square root of 1.84, do that on your calculator, square root of 1.84, that gives me 1.36. And that would equal everything on the right, but if you square root, then you can take away the squares, right? So now we have x instead of x squared over 0.156 minus 2x instead of 0.156 minus 2x squared. That equation is a lot easier to solve because it's not a quadratic equation. So I'm going to solve that now by taking 1.36, the number up front. I'm going to multiply by the denominator. So multiply this by 0.156, take away 2x. And that has to equal the numerator, has to equal x. Does anybody not really understand that algebra? We're good? Then go ahead and multiply through. So 1.36 times 0.156 gives me 0.212. Take away 1.36 times 2 would be 2.72 x's. And that equals, we have just x, but I'll put a 1x just for the hell of it. So next we're going to move the 2.72 x's to the right-hand side of the equation. So I'm going to add 2.72x to the right-hand side. So that gives me 0.212 on the left will equal 1x plus 2.72x's, whoops, is equal to 3.72x's. And now I can divide both sides by 3.72, and x will equal 0.212 take away divided by 3.72, 0.0570. molarity. Okay. For those of you who have a graphing calculator, do you want me to walk you through how to do that on the solver? Anybody want
Yes,
the
please.
solver? All right, do you want to see it, or do you want me to just walk you through by talking?
Mr. P, I don't think we're done yet.
We're not done yet, but we finished solving the equation. So I want to ask, is there anybody with a graphing calculator want me to go through how to do the solving of the equation on the graphing calculator? So I'm going to talk you through it then, okay? So on your graphing calculator, you press the math button. Stop me immediately if you get lost. So press the math button, scroll down until you see solver on the old calculator or numeric solver on the new calculator, and press enter. If you have the old calculators, then you need to press the up arrow at this point and then clear yesterday's equation. Your screen should now say equation solver 0 equals. And just like yesterday, to get your equation to say 0 equals, I'm going to show you, look at the screen here. We're solving this equation here that I've just highlighted. So to get that to say 0 equals, you'll be typing in x squared divided by blah, 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 and then you'll write minus 1.84. So if you put the 1.84 to the right-hand side, it'll say 0 equals the algebra minus 1.84. For those of us with the newer calculators, we're typing E1, equation 1, is just 1.84, the left-hand side of our equation. And then E2, the second equation, is the stuff on the right-hand side. So x squared divided by brackets 0.156 minus 2x, close bracket, squared. So the older calculator people, you wrote x squared divided by the bracket squared minus 1.84. The newer people, the newer calculator people, we wrote E1 is 1.84 and E2 is the algebra stuff. At that point, everybody presses enter. In the middle of your screen, it should say x equals, and it will show you the last time you used it, the answer. So that's not the answer to this equation, it's the answer to the last equation. So we type 0, x equals 0, as a guess for our answer. And then we press the alpha button and enter, which means alpha solve. And when I do that, my calculator says x equals 0.05699, which is 0.0570, the same answer I got here. Okay. Now, if you didn't get that for some reason, I'm not going to help you with it right now, but you can ask me at the end and we'll spend a few minutes with your graphing calculator if you're having trouble with the solver. So at this point, we've solved for x, but William pointed out that's not the answer to the question, right? So the x, though, is the amount of hydrogen at equilibrium. X is the concentration of iodine at equilibrium. So why don't we add one more thing here? I think I need to put more space on this paper. So therefore, the concentration of HI at equilibrium is going to be, looking up at your ice table, it's 0.156 minus 2x. So 0.156 minus 2 times 0.0570. Please ask if you're not sure where that came from. So 0.156 minus 2 times 0.057 gives me 0.04 molarity. Okay, 0.0420 I'll put there. So that's the concentration of the HI. But again, this bastard question, it doesn't ask me for the concentration of HI, it asks me for the mass of HI. So I need to go now and calculate the mass. I'm running out of room here, but I'm going to squeeze that in this space up here. Okay, so let's find the mass of HI at equilibrium. So I'm going to do that with unit multipliers. This is grade 11 chemistry. So I'm going to start with my volume. I'm going to take the 500 milliliters, and I'm going to use 3 unit multipliers just like we did before, but now I'm going backwards sort of. So I'm going to switch the milliliters to liters. Then I'm going to use the concentration that we just calculated to switch liters to moles of HI. Let me just 1 sec. And then with one more multiplier, we'll switch the moles of HI to grams of HI. Yes, William?
Why did you use like 500 milliliters?
The question said we have 500 milliliter flask.
Okay.
Right?
So that's where
So
all
this
the...
whole reaction is inside the 500 milliliter flask.
Okay.
So the concentration of HI at the end, 0.0420 molarity, is the concentration of HI inside the 500 milliliter flask. Right?
Okay, I get it. Thank you.
Okay. So for those of you who don't really like unit multipliers, number one, my sympathy, but you're going to use formulas. You're going to take your volume and your concentration and find moles. Then you can use the moles and the molar mass to find grams. But I like unit multipliers. This is what I'm going to do. 1 liter is 1,000 milliliters. The concentration we just calculated was 0.0420 moles per liter. The concentration of HI that we just calculated down below. And the molar mass of HI, we had that earlier, it was 127.91 grams. So 500 milliliters, 500 divided by 1,000 times 0.042 moles per liter, and then times 127.91 gives me a mass of 2.69 grams of HI. And that is the same answer we see up above. All right. There's a lot of stuff in that answer, and I can understand somebody being confused, but try to look at it as different steps. And if you're having trouble, don't just say, I don't get that question, because I can't help you with that. Try to look at the steps and say, I don't understand that step. So did you understand how we did the initial concentration of HI? Right? So if you had trouble with that, that's grade 11 chemistry. Okay, but if you have trouble with that, I can help you with that later. Did you understand how we filled in the ice table using the initial conditions and the algebra? Okay. Did you understand how we set up the Kc expression and put the algebra in? Did you understand how to use your solver on the graphing calculator, or how to solve this using algebra to get 0.0570? Did you understand that that wasn't the end of the question? We had to go get the HI's concentration. And then lastly, we had to take that and do grade 11 chem to get the mass at the end. Okay, so those are the different steps. If you didn't understand one or more of those steps, ask me later for how to help you with that particular step, okay? All right, I'm gonna stop this video recording and we'll post that later.